Good afternoon, everyone. We are the reporters from Group 2, which entitled Time Response. So the content of this PPT is Introduction, Time Response, Input Supplied System, Steady State Response and Error, Types of the Systems, Analysis of First Order System, Analysis of Second Order System, Transient Response Specification, Limitations, and last, Sums. So, our introduction is that time response of the system is defined as the output of a system when subjected to an input which is function of time. So, si time response analysis which subjected the control system to inputs that are functions of time and studying their output which are also function of time. So basically, si time response kay ga respect gyud siya sa time. Next. So what is the definition of time response? So si time response of a system is the output response which is function of the time when input excitation is applied. So si time response di ay siya, kay kaning mo ni siya ang output sa imuhang response kung ang input or excitation is applied. So si time response of a control system consists of two parts. So by the way, na two parts si time response of a control system. First is the transient response. Second is a steady state response. Mathematically, naa siya equation. So C of t is equals to C sub t of t plus C sub SS of t, where C sub t of t is equals to transient response. Then C sub SS of t is equals to steady state response. So what is unsa man day ang meaning ni kuan day transient response? So transient response is the part of response which goes to zero as time increases. So kung ga pataas na ang time, so si transient response gapa zero pud siya. Kung the more nga gataas ang time, gapa zero zero siya. So, mathematically, na siya limit t approaches to infinity. C sub t of t is equals to 0. So, see, the transient response may be exponential or oscillatory in nature. So, when we say oscillatory in nature, guys, kay move or swing back and forth at regular speed. So, si transient response, move or swing back na siya sa regular nga speed niya. So, si steady state, so, si steady state kay response is the part of the total response after transient has died. As what I've said earlier, si transient response as the time ga-increase, gapa-zero siya. So, kung ma-zero na dayon siya, diha na dayon mo occur si steady state. Kay siya na dayon ang kaning responsible sa sunod nga kuan button. So, si steady state, napud siya error. So, si steady state error, if the steady state response of the output does not match with the input, then the system has steady state error denoted by E sub SS. So si steady state error di ay ni siya mo-occur kung iyang input, ang iyang output dili magmatch sa iyang input sa control system. Mao din siya nga naa na siya steady state error denoted by E sub SS. So, si time response, a control system generates an output or response for given input. So, si control system day siya, kani ang output na siya or response nga gihatag na bitaw kani unsa gihatag sa given input sa isa ka control system, mo na pud na iyahang kuan. Mo na siya si time response. So, the input represents the desired response while the output is a actual response of a system. Best example ani niya kay kaning elevator. So, as what I've said earlier, no, si kuan di ay time response kay iyahang kuan siya oscillatory in nature. So, which means nga move or swing back and forth at regular speed. So, sa elevator kay mo pataas, mo baba, pataas pababa man na siya. So, as defined earlier, time response is the response of control system as a function of time. So, si time response analysis is divided into two parts. First is that the output is changing with respect to time. Muna siya ang first part niya, si transient response. no, kay gapataas ang time, gapataas ang iyahang ga-increase ang time, ga zero si transient response. Second is the output is almost constant. So kung almost constant na din siya, mo na din siya si steady state response. So as what you have observed sa ato ang kuan graph, na siya kuan transient, diba? Pababaw pa na siya, gapataas pa ang iyang time ana antod ma-reach niya ang iyang maximum, then magpaubos, decrease din siya, hinay-hinay din siya antod maabot siya sa steady state niya nga kuan being. So note nga the transient response is predicted with a homogeneous solution. Ganun gi-predict mo na siya nga as a homogeneous solution di ay. So it is because it describes how the system behaves before it reaches a steady state. So mo na siya ang ga-describe sa iyahang kuan kung giunsa pag steady state bito sa isa ka system. So that the total time response C sub t of t followed by the steady state response CSS of t. So as what you can observe, mo ni siya ang graph. The graph shows how the time response kani ang mag-occur o sa iyang graph. So sa ubos ana naa siya rise time. So diri siya mag-occur si transient response sa transient, diya siya mag-occur si transient response. So pagkakita na nimo diya siya sa maximum overshoot niya, pag ubos na dahil niya nga pag-ubos, naa na dahil na siya diya sa steady state. So decrement equal to A over B hantod ma steady state error. Just like an example no kanang sa aircon. Aircon di ba kabantay mo pag on ninyo kay dili pa man siya automatic nga mobugnaw. As the time pass by, nga ga-increase ang time, ang iyang kuan na ang system niya di ba gabugnaw na dayon siya. Dito si transient response ga-occur katong gapataas wa tawang temperature ay gapakold hantod sa reach niya ang maximum niya magpaubos din na siya until mas maabot na din niya ang steady state niya. So ang aircon kay inverter naman dahil na siya, magdiya na din siya mag-on and off. Nga ma-constant na din siya, steady state na dayon. So next. So input supplied to system. So for time response analysis of control systems, we need to subject the system to various test inputs. So ang kaniyang kuanday, control systems dapat pud ato pud siyang i-test sa mga various test inputs nga pwede. So si test input signals are used for testing how well a system responds to known input. Some of standard test signals that are used are first impulse, step, ramp, parabola, sinusoidal. So common naman kayo siya sa tuano na agian naman nato ni sa high school ug sa first year college kani siya mga kuan. So si impulse input. So unsa man si impulse input dai? So it is a sudden change input. An impulse is infinite at t is equals to 0 and everywhere else. Sudden change input then is a impulse input. So over ani si r of t is equals to delta of t is equals to 1 or equal to 0. In Laplace domain, we have Laplace r of t is equals to 1. So as what you can observe na there is a right nga portion, right? Oh. Kay makita nimo ang graph. The graph shows nga ang iyang kuan sudden change input siya. So si step input, it represents a constant command such as position. Like elevator is a step input. So r of t is equals to u of t is equals to a or equal to 0. Laplace of r of t is equals to a over s, where t greater than or equal to 0. Otherwise, makita nimo sa iyahang graph, no? Constant naa sa babaw, naa sa 1 ang iyahang kuan line. So with straight line na siya kay constant naman ang iyahang command. Then si ramp input, this represents a linearly increasing input command. R of t is equals to at or equal to 0. Laplace r of t is equals to a over s squared, where a is equal to 1 then unit ramp, where t is greater than or 0, a slope, t is less than 0. So diri na punta sa parabolic input. So unsam din ni si parabolic input? So it is a rate of change of velocity is acceleration. Acceleration is parabolic function. So r of t is equals to a t squared all over 2 or equal to 0. Laplace of r of t equal to a over s cubed, where t is greater than or equal to 0, t is less than to 0. As what you can observe, sa right portion na siya graph. Ang graph niya shows nga gapakiwi ang iyahang kuan, iyahang line. So, si parabolic manggod kay ga pa U-shape manggod na siya. So si sinusoidal input na pod. So input of varying and study the system frequently responds. So R of t is equals to A sin Wt, where t is greater than or less than 0. So what you can observe, ang kaning graph, it shows a sine wave, no? Sine wave na siya. So next dayon, si steady state error. So steady state error is the difference between the input and output of the system during the steady state. For accuracy, steady state error should be minimum. We know that naa siya equation. So unsa man niyang equation? E of s over r of s is equals to 1 over 1 plus g of s h of s. So where si r of s is the reference input in the Laplace domain, si E of S, the error signal in the Laplace domain, which is the difference between the reference input, Rs, and the output of the system after feedback. So G of S, the transfer function of the forward path, while H of S, the transfer function of the feedback path. So muna siya yung meaning sa mga iyahang unit dire. So the steadies, so dire din, ato na din na siyang i-cross multiply. So what you can see, i-multiply din siya, din ang si R of S, diya na din siya sa baba. Ang result din ni error S is equals to R of S over 1 plus G of S, H of S. So the steady state error of the system is obtained by final value theorem. So final value theorem na niya kay si E of SS, steady state error niya siya, equal to limit t where approaches to infinity, E of t is equals to lim S approaches to 0, S that times E of S. Kabalo naman ta nga si E of S is R of S over 1 plus G of S times H of S. So ato na din na siyang isulod dira. So diri na po din sa for unity feedback, si H of S is equal to 1. Kung equal to 1 si H of S, ang iyang equation is that E sub SS is equals to limit S is approaches to 0, S times R of S over 1 plus GS. So as what you can observe, nawala si H of S. It is because si H of S is equals to 1. Gitimes na lang din na siya, may mo din sa G of S ang remaining niya. So next.
Of static error coefficients with a focus on the positional error constant, K sub p, this constant measures the system's ability to handle a unit step input without a significant error in the steady state. The unit step input, represented as R of S equals to 1 over S, is a common test signal in control systems. And the steady state error, the formula provided shows the calculation for the steady state error for a system with a unit step input. It is calculated as steady state error equals to 1 over 1 plus K sub P, where K sub P is equals to the limit S approaching to 0, G of S times H of S. Here, G of S and H of S represent the open loop transfer function of the system. A higher Q, I mean, so a higher T sub P values implies a smaller steady state error, meaning the system can follow the input more accurately in the steady state. This measure helps assess the performance of control systems in handling constant inputs. Velocity error constant, represented as K sub V. The slide explains the concept of the velocity error constant. which is used to measure the steady state error of a system with a unit ramp input. The steady state error for a unit ramp input can be represented as steady state error equals to the limit s approaching to zero s times r of s times 1 over 1 plus g of s times h of s. For a unit ramp input, r of s is equals to 1 over s squared. This changes the equation for the steady state error shown in the slide. The derivation on the slide shows how to substitute r of s is equals to 1 over s squared and simplify to find the expression. The steady state error is equals to the limit s approaching to 0, 1 over s times g of s times h of s is equals to 1 over k sub v, or the velocity error constant. This final form indicates the steady state error for a ramp input is inversely proportional to the velocity error constant. The slide concludes with the definition of the k sub v, where k sub v is equals to the limit s approaching to 0, s times g of s times h of s. This coefficient represents the system's ability to track a ramp input. A higher k sub v implies a lower steady state error for a ramp input, meaning better performance in terms of following a steadily increasing input. So acceleration error constant, represented as k sub a. Similar to the previous constants, this one deals with unit parabolic inputs. The formula here determines the steady state error for systems with parabolic input by using the acceleration error constant k sub a. And then in the steady state error for different types of systems, this slide explains where the steady state error varies based on the type of system and type of input. For example, type 0 systems with unit step inputs have finite or my boundary siya. So in steady state error but with ramp or parabolic inputs, the error becomes infinite. So in type 1 system with unit step and ramp inputs, this slide describes the behavior of steady state error with different inputs. For unit step inputs, the steady state error is 0, while for ramp inputs, it is finite. The slide shows calculation that illustrate this distinction. So the type 1 system with unit parabolic input, the slide shows that the steady state error becomes infinite, implying that parabolic inputs aren't suitable for this system type. This slide concludes that for type 1 systems, step and ramp inputs are acceptable, but parabolic inputs lead to unmanageable errors. So summary for type 0 and type 1 and type 2 system. This slide provides summary table that shows the steady state error values for different system types. Each cell in the table indicates the steady state error for a particular system type and input combination. For example, a type 0 system with a unit step input has a finite steady state error, while the error for a unit ramp input is infinite. Example, finding static errors constants for a given system. This example demonstrates how to calculate static error constant for a given system based on its transfer function. The slide walks through the calculation to find these constants and then uses them to determine the steady state error for step, ramp, and parabolic inputs. So an example for unity feedback system, this example explains how to calculate the static error coefficients. For a unity feedback system with a specific open loop transfer function, each coefficient is derived using limits of the transfer function as s approaches to zero, which which helps in determining the system's steady state error response for various types of inputs. Then the next slide will be analysis of the first order system.
Hello everyone. My name is Neljan Arbuyante and today I'll be the one to report about the analysis of first order system. So, analysis of the first order system for step input function. So, consider our first order system as shown in this figure. So, in this figure, we can see a feedback loop system which has an input RS and our output is CS. And we have a GS which is our forward path and our HS is our feedback path. So, our GS here is equals to 1 over TS. And our HS here, which is our feedback forward, is equal to 1. So here we have CS over RS, which is our transfer function for the figure here, which is a closed loop. So it is equivalent to the G over 1 plus GH. And if we substitute the value of G here, G is equals to 1 over TS and H is equals to 1, then therefore we can conclude that our transfer function is equals to 1 over 1 plus Ts. So next, for our step input, we have here R of t is equals to our U of t when t is greater than 0. So if we take the Laplace of our step input function here, we will get 1 over s. But if we go back to the our transfer function, which is cs over rs is equal to the 1 over 1 plus ts, then we have to get our by solving the output signal or our cs, we must multiply both sides by rs. So our rs is equals to 1 over s, so we have to go to the next slide please. So here, so atong RS man is equals to 1 over S. So i-multiply na to siya sa to ang transfer function sa closed loop. So mao ni siya 1 over 1 plus TS multiplied by 1 over S. Then we need to use partial fraction in order for us to simplify it. So if at ano na siya, A is over S plus B over S plus 1 over T. So in solving A, we have to multiply s plus cs and let s equals to 0. Therefore, our a is equals to 1. In solving b, atong buhaton is kung ano to ang s plus 1 over t, that is a partial fraction, multiply na to siya sa to ang cs, our output, and we have to let s is equals to negative 1 over t in order for us to get negative 1. Next. So, to continue, na naman tayo, ang equivalent sa A is 1 and equivalent sa B is negative 1. So, here na siya. Ato ang output is equals to 1 over S minus 1 over S plus 1 over T. Taking the inverse Laplace of that, 1 over S, 1 over S minus the inverse Laplace of 1 over S plus 1 over T. So, our output is equal to 1 minus e to the negative 1 over T times its time domain. So here we have a graph. By using our time domain from the transfer function of the closed loop. So what if atong e input na ni? So if our t is equals to 1, i-input na to dito siya sa atong time domain, makakuha tag 0.632. And if our t next is 2t, then ato ang output kay mag-equal siya sa 0.86. So mag 3t hanto din na siya nga maabot siya sa infinity, and from infinity it will approach to 1. Next. Analysis of first order system for unit impulse. So, sa tong input unit impulse function RS, so our input is equal to 1. So, atong RS na is equal to 1 na siya para sa impulse. So, atong output is equal to the 1 over S plus 1. Balik ta sa itong gisolve ganiha, itong gi-substitute lang. Dayon plus RS, times RS. So, atong RS is equals to 1, gi-multiply na to siya. Dayon, maka-unsa din ta nga, ato din i-factor out ang ST plus 1. So, i-factor out na to siya, makakuha siya 1 over T multiplied by 1 over S plus 1 over T. So, ato na sa siyang i-inverse to plus that. So, constant man ng 1 over T. Dayon, inverse nato ng 1 over S plus 1 over T. Then we get 1 over T e to the negative T over T. So, next. So, analysis of first order system for unit ramp function. So, we know nga ito ang closed loop function is equals to 1 over st plus 1. Dayon, ato din i-multiply both side ang rs para unsa na isolate ito ang cs or output. Dayon, ato ang input unit ramp is equals to the 1 over s squared. Dayon, ato din siyang i-multiply nato siya sa tong unsa gani ang function nato sa closed loop. Dayon, makaget tag 1 over s squared multiplied by 1 plus st. Dayon, using partial fraction again, we can get this format. So 1 over s squared minus t over s plus t multiplied by 1 over s plus 1 over t. So next. So, kung na-inverse na plus na to siya, convert na to siya from frequency domain to time domain, then we can get t minus t plus t e to the negative t. Our unsa man na siya, error signal, di ba? Ang atong error signal is equals to our input minus our output. So, ibutang na to siya. So, t, so man na to ang r. So, minus t plus t e to the negative t over t. So, man to atong output ganiha in time domain. So, we can get, from simplifying this, we can get t, factor out, times 1 minus e to the negative t over t. Then, we will find its steady state error for using this formula. So, the limit when t approaches infinity, t minus t e to the negative t, which is the time domain over t, is equals to t. So, the steady state error is equals to t. So, and t is our steady state error, where t is the time constant of the system. So, constant, yun na siya, time constant. For smaller time constant, steady state error will be small and speed of the response will increase.
So I'll be explaining the analysis of the second order system. Next. So the block diagram shows a standard second order system with a transfer function of C of S over R of S is equals to omega n squared over S squared plus 2 zeta omega ns plus omega n squared, where C of S is the output, R of S is the input, omega n represents the natural frequency, and zeta is the damping ratio. So for analysis, we consider a unit step input. So ang R of S is equals to 1 over S, and we are going to plug the R of S into the transfer function. And then we would have C of S is equals to 1 over s multiplied by omega n squared over s squared plus 2 psi omega ns plus omega n squared. And that would be our first equation. So we replace the denominator of the first equation by s plus psi omega n squared plus omega n squared multiplied by 1 minus psi squared. And then we'll have the second equation, which is the C of s is equals to 1 over s multiplied by omega n squared over s plus psi omega n squared plus omega n squared times 1 minus psi squared. So we break the equation by partial fraction. So we could find the domain response, and the fraction decomposition on C of s, which is C of s is A over s plus B of s plus C over s plus zeta omega n squared plus omega d squared, where after we put the partial fraction, we would have 1 over s multiplied by omega n squared over s plus psi omega n squared plus omega d squared is equals to A over s plus B over s plus psi omega n squared plus omega d squared, which is our third equation. So we multiply equation 3 by s plus psi omega n squared plus omega d squared. And then we'll have s is equals to negative psi omega n minus j omega d. And b is equals to omega n squared over s. And the next one would, following that equation, would be the omega n squared negative psi omega n minus j omega d, would bring us to the equation d is equals to negative psi omega n plus s plus psi omega n is equals to negative s plus 2 psi omega n. And we could rewrite the equation as equation 1 as C of s is equals to 1 over s minus s plus psi omega n plus psi omega n over s plus psi omega n squared plus omega d squared. For the next, we apply the inverse Laplace transform to get the domain response, to get the time domain response of C of t, where C of t is equals to 1 minus e to the power of zeta wn t multiplied by the cosine omega dt plus zeta over square root of 1 minus zeta sine omega dt. In this expression, the e to the power of negative zeta omega nt, it represents the exponential decay due to damping, and the cosine omega dt and sine dt represents the oscillations in the damped natural frequency WD. So next, so to make the response clear, i-express na to ang terms sa phase angle, and ato siyang i-define as tan phi is equals to tan phi is equals to the square root of 1 minus zeta squared over zeta. And we can rewrite the CT as the C of t as 1 minus e to the power of zeta omega nt over square root of 1 minus zeta squared times sine omega dt plus the phase angle, which then shows the damped sinusoidal behavior more clearly. So for calculating the error signal, which is the difference between the input R of t and output C of t, since R of t is equals to 1 and 1 is a unit step, then we'll have E of t is equals to R of t minus C of t. So i-substitute nato to ang expressions nga ato ang dimension sa taas. And then makuha nato ang E of t is equals to E to the power of zeta omega n t over square root of 1 minus zeta squared sine omega dt plus the phase angle.
So, analysis of second order system for step input. The poles are real if square root of psi squared minus 1 is greater than 0. If they lie on the real axis and distinct. While real and equal if square root of psi squared minus 1 is equal to 0. If complex, kay square root of psi squared minus 1 is less than 0. Poles are in the second and third quadrant. So here, relation between psi and the poles locations. So number 1 is 0 is less than psi and less than 1. So under siya sa dump, mo yung step response niya. And so is the pole location sa under dump. Sa 2 is psi is equals to 1. Critically dump. Mo po ni siyang kuwan naka step response niya o yung pole location. Number 3 is psi is greater than 1. Overdump siya. So you can see the pole location and the step response also. Psi is equals to 0 under dump system. Undump system rather. Mo po niya ang pole location. Transient response specifications. Specifications for a control system design often involve certain requirements associated with the time response of the closed loop system. The requirements are specified by the behavior of the controlled variable or by the control error on well-defined test signals. The most important test signal is a unit step on the input of the control system, and requirements are placed on the behavior of the controlled variable. Time response specification. The maximum overshoot is the magnitude of the overshoot after the first crossing of the steady state value 100%. The peak time is the time required to reach the maximum overshoot. The settling time is the time for the control variable first to reach the thereafter remain within a prescribed percentage of a steady state value. Common values of are 2%, 3%, or 5%. The rise time is the time required to reach the first steady state value 100%.
So first, let's begin with delay time. Delay time refers to the period it takes for a system output to begin responding after a step input is applied. It specifically measured the duration until the output reaches 50% of its final value. This parameter is important because it indicates how quickly a system can start to react to changes. And it has a formula of T sub D is equal to 1 plus 0.7 zeta over omega sub n. Second, we have rise time. Rise time, denoted as T sub R, is a critical time response specification in a control system that measures how quickly a system output responds to a step input. Specifically, it is defined as the time required for the output to rise from 10% to 90% of its final steady state value. Understanding rise time is essential because it reflects the speed of the system's response. A shorter rise time indicates that the system can quickly adjust to changes, which is particularly important in applications requiring rapid reaction. And it has a main formula of T sub R. Please go next, Gipa. And it has a main formula of T sub R is equal to pi minus arctan square root of 1 minus zeta squared over square root of 1 minus zeta squared over omega sub n. Understanding rise time is essential because it reflects the speed of the system response. A shorter a shorter rise time indicates that the system can quickly adjust to changes. And for the peak time, it is crucial parameter in control system that measures the time it takes for the system output to reach for its maximum value after a step input is applied. This parameter is significant because it indicates how quickly the system responds to changes and provides insight into its dynamic behavior. In applications where rapid responses are essential, understanding peak time helps engineers evaluate whether a system is adequately tuned for performance. And there is some practice example of it, which is automotive application. For example, in vehicle dynamics, a short peak time is essential for quick acceleration and responsive handling, ensuring that the vehicle performs optimally during maneuvers. And it has a formula of if the peak time to first overshoot put n is equals to 1, we have t sub p is equal to pi over omega sub n square root of 1 minus zeta squared. For the first minimum, undershoot occurs at n equals to 2. T is equals to 2 pi over omega sub n square root of 1 minus zeta squared. For the For the maximum overshoot, it is a key performance metric in a control system that quantifies how much the system output exceeds on its desired steady state value during the transient response after a step input is applied. Specifically, it measures the maximum deviation of the output from the final value before the system settles. Understanding maximum overshoot is crucial because it directly impacts system stability and performance. Excessive overshoot can lead to undesirable effects such as oscillations, instability, or even damage in mechanical system. Therefore, controlling maximum overshoot is essential for achieving desired performance levels in various applications. The formula for the maximum overshoot, denoted as m sub p, can be approximated for a second order under time system as follow. So, mo ni siya iyang formula. In this formula, zeta is the damping ratio. This equation illustrates that as the damping ratio increases, the maximum overshoot decreases. A higher damping ratio results in a more stable system with less overshoot, which is crucial for ensuring that the system behaves predictably and reliably. Next we have settling time, which measures the time required for the system output to remain within a specific percentage, usually 2% or 5% of the final value after the initial response. And we have the formula of 40 is equals to 4 over zeta omega. Here, zeta is the damping ratio and omega is the natural frequency. A shorter settling time indicates a system that stabilizes quickly after a disturbance, which is essential for maintaining performance in fast-changing environments like in process control or telecommunication. And finally, let's discuss about the steady state error. This is the difference between the desired output and the actual output as time approaches infinity. Understanding this error is crucial for assessing how accurately the system can follow a given input. And we have the formula i- which is in this formula, as you can see in the PPT, R of t represents the reference input or the desired output, while Y of t is the system output over time. This equation helps us understand how accurately the system can follow the desired input in the long run. A smaller steady-state error indicates better performance and accuracy of the control system.
Limitations of time domain analysis. Control system analysis is carried out in either time domain or frequency domain. The domain of analysis depends largely on the design requirements. The analysis is the frequency domain is very simple and quick. Stability determination using a frequency response plot can be done in very quick time with no effort. In time domain analysis, the analysis becomes cumbersome for systems of high order. In frequency domain analysis, the order has a little effect on the time or effort of analysis. So, for example, the open loop transfer function of a servo system with unity feedback is given by Gs equals to 10 over S plus 2 times S plus 5. So, determine the damping ratio and natural frequency of oscillation. So, what is the percentage overshoot of the response to a unit step input? So, solution, given that Gs is equal to 10 over S plus 2 times S plus 5 and Hs is equal to 1, the characteristic equation will be 1 plus Gs times Hs equals 0. So we substitute the value of Gs and Hs, we can get the 1 plus 10 over S plus 2 times S plus 5 equals to 0. So S squared plus 7S plus 20 equals 0. Compare with S squared plus 2 zeta times omega sub n S plus omega squared sub n equals 0. We get the value of omega squared sub n equals to 20 and 2 zeta omega sub n equals to 7. Therefore, omega sub n is equal to the square root of 20 or 4.472 rad per second. So 2 times zeta times 4.472 equals to 7. Therefore, zeta is equal to 0.7826. So m sub p is equal to e raised to negative pi times zeta over square root of 1 minus zeta squared equals to e raised to negative pi times 0.7826 over square root of 1 minus 0.7826 squared times 100, we get the value of 1.92%. And here in example 2, a feedback system is described by the following transfer function. Gs is equal to 12 over S squared plus 4S plus 16 and Hs is equal to Ks. So the damping factor of the system is 0.8. Determine the overshoot of the system and value of K. So the solution, we know that Cs over Rs is equal to Gs over 1 plus Gs times Hs. Cs over Rs equals to 16 over S squared plus 4 plus 16K times S plus 16. S squared plus 4 plus 16K times S plus 16 equals to 0. It is the characteristic equation. Compare with S squared plus 2 times zeta times omega sub n times S plus omega squared sub n equals to 0. So therefore, omega squared sub n equals to 16 and 2 zeta omega sub n equals to 4 plus 16K. And 2 times 0.8 times 4 equals to 4 plus 16k. So therefore, we have the value of omega sub n is equal to 4 rad per second and k is equal to 0.15. So we get m sub p equals to e over negative pi zeta over square root of 1 minus zeta squared times 100 is equal to e raised to 1 ay negative pi 0.8 over square root of 1 minus 0.8 squared times 100. So the value of m sub p is equal to 1.5%. Thank you.